Three hand rules so far. The first one we called the wire grasp rule. And the wire grasp rule, if you remember, is simply used to find the magnetic field that's caused by a moving charge. Moving charges generate magnetic fields. Maybe there's an external magnetic field, maybe there's a force, whatever. We don't care about that if we're using the first rule. All we care about is the magnetic field caused by the moving charge. And you remember how to use that rule, right? Thumb, usually the left thumb, but sometimes the right thumb in the direction of the moving charge. Bend your fingers a little bit, a lot, it doesn't really matter. Your fingers will point in the direction of the magnetic field caused by that moving charge. Then we had the coil rule. And the coil rule, remember, that's the easiest one to kind of understand when to use it, because generally when you have a coil of wire or a solenoid, you're going to use the coil rule, right? And that's used generally, though, to find the direction of the magnetic field inside or outside of the solenoid. Maybe it's to find the polarity of the solenoid, something like that. Okay? Something to do with the magnetic field in or around a coil or a solenoid. The third rule that we learned yesterday is called the deflection rule, the hand rule for deflection. And the deflection rule is used when we have an external magnetic field and there's something involving a force, a magnetic force, because of that external magnetic field and the moving charge. So charge moves through an external magnetic field. There's going to be a magnetic force. We can find the direction of that magnetic force by that deflection rule. It says thumb in the direction of the particle, always 90 degrees, right? Thumb and fingers always 90. Thumb in the direction of the moving charge, fingers in the direction stretched out this time in the direction of the external magnetic field. My palm will automatically point in the direction of the force. Now, we also learned how to find the direction of that, the magnitude of that force, and that was by using this equation, F is equal to Q V B. We should, by rights, although we often don't write it just because we're trying to save a little bit of time or getting a little careless, whatever, we should, by rights, put that little upside down T beside the V as a subscript here. How come? What does that mean? Yep. Yeah, it means that in order to use this equation or the hand rule for deflection, either one really, okay, the particle must be moving perpendicular to the magnetic field. That's a big word, right? We said that yesterday, that the word perpendicular is a big word in this unit and in the next unit as well. We said that probably about 90% of the time, if you get a question where you have to identify a direction in this unit or in the next unit, the answer will be perpendicular. And if you're going to have to guess on a question involving direction, parallel, perpendicular, whatever, the answer is almost certainly going to be perpendicular. So this equation and the hand rule are both valid when the particle is moving perpendicular to the magnetic field. What do we do if the particle is moving parallel to the field? Like they're both this way, or one's this way and one's this way. They're parallel. Then the force is zero. So then it becomes even easier because you don't have to do anything, right? The force is zero. You don't have to do a hand rule. There's no equation when the force is zero. What do you do if the particle is moving this way and the magnetic field is this way, 30 degrees away from it? No, the force isn't zero. There is a value of the force, but the good is we don't have to deal with that, right? It's not hard to deal with. Okay, there's an equation that's relatively simple to deal with it. It's just that we don't have to deal with it, so we can be confident that we're not going to see that question, okay? Just know that the force is somewhere in between, the value is somewhere in between 0 and whatever you get when you multiply Q times V times B. All right? All right. We had some questions for homework. 1 to 8 involved the direction of the magnetic fields, or direction of magnetic fields or magnetic forces. And questions 9 and 11, which I also assigned on worksheet number 11, involved some calculations. I want to go over those questions here now. Okay, let's do 4 of those questions, 4, 7, 8, 11. The first 2 involve the hand rule, the last 2 involve calculations. Number 4 says an alpha particle, I'm going to circle that, remind me that it's a positive. If I got to do a hand rule, which odds are here I do, it's going to be a right hand rule. Travels to the north through a magnetic field that points to the west, which way does the magnetic force point? Remember yesterday we said we're not going to lose any sleep over trying to figure out which way is actually north from us. Okay, we know that truly this is north, or geographic north, and this is south, this is west, this is east. But if we're in a room where we can't see out the windows and we kind of get turned around and we don't know which way is really north, it doesn't really matter as long as we say that west is to the right of north and east is to the left of north, right? So yesterday when we did it, we said that was north. Today we're going to pretend that that's north, okay, just to show you that it doesn't really matter. So that's north. Number 4, which says we've got this particle, this alpha particle that's going to the north. I'm going to stick my right thumb to the north. Right, this is north for us. Right thumb to the north. Magnetic field is pointing to the west. Well, the west is to the left of north, right? Hey, you picture the map of Canada that we put up on the board yesterday? Okay, British Columbia is to our west, and it's to our left. So we're going to say thumb to the north. We're going to say fingers to the west, right, to the left and north, and my palm is going to point which way? Up. Up the page? Up from the earth, which, because the earth stays where it is, then we can just say up if we want. Okay, so the answer for that one is up. Let's do number 7 now as well. An electron travels east. An electron travels east, experiencing magnetic force to the north. Which direction is the magnetic field point? Let's make this north again. Okay, let's say the electron is traveling to the east. So to our left is east. Remember, looking at the map of Canada, Nova Scotia is to our left, and Nova Scotia is to our east. So we're going to say thumb is going towards Nova Scotia. Okay, fingers. Oh, we don't know which way our fingers point. We want to find that, right? Which way is the field? We know our palm points, the magnetic force, or our palm points towards the north. So we're going to say thumb to the east, palm to the north, fingers are going to point downwards. So the magnetic field here, magnetic field is down. 8 says an alpha particle, it's positive, so it's right hand, traveling into the page, experiences a magnetic force to the right of the page. Thumb into the page. Palm is my force, not fingers. Palm is my force to the right of the page. Fingers point. Say it again. Say that again. Up the page, toward the top of the page. Right, Daniel?
You said for 7 that the answer is up.
Did I? I said 7 was up? What did I say in my answer key here? I did say up. So let's do that again, and let's do number 7 again to see if I made a mistake on my answer key or whether I made a mistake just now. 7, it says an electron traveling to the east. Okay, so we'll make that north. East. Oh, yeah, you're right, yeah. Yeah, I'm getting my geography mixed up. Yeah. So I was right on my answer key. Yeah, east is, so this is north. East is to my right. Okay, I'm picturing the map of Canada right now in my head. Can you see it? Kaylee, can you see it? Okay. What color is it? Never mind. So we have our particle going to the east, okay, towards the right. We have a force to the north, and it is up, as I said when I gave you the answers there. Thank you for pointing. Thank you for pointing out my mistake for the world to hear. Good? And let's take a look at number 11 as well. Number 11 says an electron is traveling through a perpendicular magnetic field. That just means that we're allowed to use the hand rule. We're allowed to use the equation. Here's the magnetic field strength, 10 to the minus 1 Tesla. Does that seem reasonable? Yeah, it is. It's strong, right? It's about 10 times stronger than the average bar magnet, but it's certainly possible, certainly reasonable. Here's the force. How fast is the electron moving? We're just going to say F is equal to QVB. V is equal to F over Q times B. So my force is 4.50 times 10 to the negative 14 newtons. Charge is 1.6 times 10 to the minus 19 coulombs. Somebody asked me yesterday in one of the two classes whether we sub the sign of the charge in here. Do we? No, we never sub a negative or positive for a type of charge into the equation. Always leave it. 3 times 10 to the minus 1 Tesla. We do the math there, and we end up getting 9.38 times 10 to the 5 meters per second. Is that a reasonable speed for a charged particle? Usually charges move at 10 to the 5, 10 to the 6 meters per second. They can move like a lot slower, and they can even move up to 3 times 10 to the 8 meters per second, the speed of light. But this is right in the range that is most common, 10 to the 4, 10 to the 5, 10 to the 6 for moving charges. All right? Good? Let's take a look at not just the force that acts on these charges as they move through the magnetic field, but what happens to them as a result of that force. I've got a bunch of X's drawn on the board here right now. Those X's are going to represent for us a magnetic field. So that magnetic field in this case is pointing which way? Away from us or into the page. Good. There's a uniform magnetic field here pointing into the page. We've got a charged particle represented by this circle here. It's a negatively charged particle, and it's traveling this way, to the right. In this diagram that I'm about to draw here, red is going to represent the velocity. So which way is it moving is going to be represented by red. We're going to say that blue is going to mean, whoops, can't spell blue, which is kind of ironic since I'm writing it in blue. Blue is going to represent the direction of the force. What's the direction of the force on this negatively charged particle right now? How do you find it? It's the deflection rule, right? Thumb in the direction of the particle, okay, which is to the right. Fingers in the direction of the field, which is into the page. Palm points down the page. Agree? So the magnetic force on this is down the page. Okay. What's going to happen to this particle's path as it is moving to the right but experiences a force down the page? Where's it going to go?
Down.
Is it going to go straight down?
No.
Nope. Is it going to go straight to the right?
No.
No. Where's it going to go?
Parabola.
Somewhere in between. Somewhere in between, okay? Hold off on the exact shape for now, okay? It's going to go somewhere in between. So let's say that this particle is now right here. Now it's moving this way. Right now it's moving, actually, no, let's redraw that here. Now it's moving this way, somewhere in between here. Thumb, direction of the particle, fingers, direction of the field. Which way is it pointing now? Which way is the force? Kind of down and to the left here. Well, now it's going to go somewhere in between, right? Thumb in the direction of the particle, fingers, direction of the field, palm points to the left of the page. Where's it going to go now? Somewhere in between here. Thumb in the direction of the particle, fingers in the direction of the field, palm points up this way. What do you notice about this? What do you notice about the force? The force, the blue force, is always pointing towards the middle. Perpendicular, yes, perpendicular, but always pointing towards the one spot right here. That one spot is the center of a circle. The path of this particle is circular. The path of a charged particle in an electric field is a parabola. The path of a particle in a magnetic field, as long as they're perpendicular, is a circle. Now, because the path is a circle, and we know the path is a circle for as long as it's in the magnetic field, it was yesterday, it is today. On all those questions you did for homework last night, it was a circular path. You just didn't need to know that it was a circular path, but it would have been a circular path. Because we know that it's in a circular path, we can continue to use this equation that we learned yesterday, but we can also use now a new equation. Want to take a stab at what it is? You remember that one? Why can we use this one? What equation is that? FC stands for centripetal force, the force that acts toward the center of a circle. Remember we said in physics 20, the centripetal force is always caused by something else? The Earth goes around the sun, the centripetal force is caused by gravity. The electron goes around the nucleus, it's caused by the electric force. Okay, when I swing my keys, if I can find them, when I swing my keys around my head, the centripetal force is caused by the tension in the string. When a car goes around a turn, the centripetal force is caused by friction. The centripetal force is always caused by something. Here, the centripetal force is caused by magnetism. So we can still keep using this equation that we used yesterday. That hasn't changed. But now, if we need to, we're also able to use this new equation, F is equal to mv squared over r. Honestly, what happens a lot in these questions now is that we end up using a combination of them. Fc equals Fm. Or in other words, mv squared over r equals qvb. So, three options. There's the first one that we learned yesterday, there's the second one, and then there's the combination of the two. Generally, if a problem doesn't mention anything about the path or doesn't mention anything about the radius, you're probably going to use the first one just like you did yesterday. If it does mention something about the radius or the path, you're probably going to use the last one. Remember, they're all valid. We're just saying that odds are you're going to use the first one or the last one depending upon what you're given. Just remember that second one, the centripetal force equation, you can use by itself as well if it seems to fit the givens. Now, one more little thing that I'll draw your attention to before we do an example here. The centripetal force equation, mv squared over r, you remember that, you recognize that from physics 20, right? The good news is you've done it before, quite a bit in physics 20. The bad news is it's not on our data sheet per se. If you look at your data sheet, you're not going to see that. But what you are going to see is this. Centripetal acceleration is v squared over r. And you'll see acceleration is equal to F over m. If you combine those, v squared over r equals F over m, then you end up getting F is equal to mv squared over r. Does that make sense? So you can remember this equation, F is equal to mv squared over r, or you can figure out this equation from the two equations that actually do appear on your data sheet. Just a word of caution though. Most times people get this equation correct, but there is a relatively common mistake that people will make, not an unheard of mistake for sure. People will say sometimes 1/2 mv squared over r. Where do you think that confusion comes from? Kinetic energy, right? Okay, they're getting two different equations mixed up. And sometimes people will say mv squared over r squared, which comes from Coulomb's law or Newton's law of universal gravitation, right? The r squared thing. So either remember it or derive it, but make sure when you do that you get it right here. All right, let's do an example. The example says, an electron is moving with a speed of 4 times 10 to the 5 meters per second to the right through a magnetic field that's directed into the page. Particle is moving to the right magnetic field is into the page. They're perpendicular, right? So everything we've learned so far applies, the equations, the hand rule, and so on. What's the radius of the path of the electron, and in which direction is it going to bend, up or down? Let's figure out the radius first. Since we're looking for radius, odds are we're going to do this. Fc equals Fm. Remember that if it doesn't work for us, we're allowed to use either of the equations by themselves, but when you're looking for radius, usually you combine them. Fc equals Fm. We're going to say mv squared over r equals qvb. We're going to simplify this a little bit by canceling out a v on both sides. See that? On the left side, there's two v's, like v squared. We can cancel out one of them. On the right side, there's one. We can cancel out it. So we've got mv over r equals q times b. You want to get r by itself? Take it up to the top by multiplying. Take qb down by dividing. So mv over qb equals r. It's an electron, so the charge is 1.6 times 10 to the minus 19 times b, which is 2.5 times 10 to the minus 2 Tesla. And we do the math there, and it works out to be 9.11 times 10 to the minus 5 meters. But does it curve up or down? We know it goes in a circle upwards or downwards. Thumb in the direction of the particle, fingers in the direction of the field, palm points which way? Down. We don't need to keep doing it like we did back on this page, because we know that if the force is downward, it's going to end up going in a circle downward. So it ends up going like this. Remember, charged particle in an electric field, perpendicular that is to an electric field, goes in a parabola. Charged particle perpendicular to a magnetic field goes in a circle. All right, I'd like you to take a look now for the next little while here at a few questions here. This is going to be worksheet number 12.